Jamin Vandenhoek, the lead at the Conflict Ecology Lab at Oregon State University. It is a huge privilege to have you on the show.
Thanks so much, Wilfred, for the invitation.
Okay, so you are a rare occurrence on the show. You might be recognized by the general public from some TV appearances over the past couple of years. So yeah, I really look forward to getting into what it was like to be in front of the camera a bit later on. But sure. I think, yeah, what we can do is, I guess, get straight into, from a technical perspective, what kinds of technology, sensors, algorithms, analytical approaches that you unleash on some of the conflicts, humanitarian situations around the world that your lab looks at and provides insight regarding.
Yeah, thanks. Well, we work with different kinds of satellite imagery in different kinds of conflict and disaster settings. We primarily work with open access data. So there's nowadays that tends to be the European Space Agency Copernicus satellites. So Sentinel-1, Sentinel-2, that'd be radar or optical systems. Those are some of our go-to right now. Historically, of course, we've used a lot of Landsat data, NASA Landsat data that goes back to the 80s, where we have sort of consistent annual data sets. So we tend to use this open data. One of the reasons we tend to use that is because it's that means our methods are reproducible. Other people can take the same data that we have access to and do their own thing with it, adapt or apply the methods as they see fit. Obviously, it's free. That's a big plus for any of these data sets. We do use commercial data, private data, say from Maxar or Planet, or we're starting to test the waters some with the commercial satellite radar data as well. Companies like ICEYE or Umbra. Those products are great in their own in their own right. A lot of our questions, though, just go back farther in time to when those systems weren't operating. So we still rely on these open data that have been collected consistently year after year after year for quite a long time. But it's a whole slew, right? We have sensitivities, different sensitivities from different systems for urban damage or forest cover change or agricultural damage, looking at ocean conditions. All of these require different modalities. So just over the time, we've worked with different systems. We've worked with space LiDAR, space radar, aerial LiDAR,
even LiDAR.
All sorts of different things. Yeah, even LiDAR. We worked with a study looking at reservoir volume change in Brazil, and worked with the ICESat radar system, LiDAR system for that, which was kind of a troubled system at the time, but it was the first space-based laser. And I have colleagues that work a lot with the JEDI system now, which is, totally revolutionized global forest carbon mapping. So yeah,
it's one called JEDI.
JEDI, GEDI.
Okay.
But yeah, they do call themselves the Knights of JEDI, the main researchers on the team.
Awesome. Okay.
Yeah.
Everyone is suddenly Googling. Okay. All right. So that is the definition of an answer about your multi-sensor approach. You mentioned applications to do with agriculture. You were looking at levels of reservoirs. There was some mention of conflict zones. Could you, and you mentioned things like ICEYE, Umbra, those have been guests on the show. I'm still working on someone from Landsat. Maybe after this, we can finally convince them that it's a good show. So what is the decision-making behind choosing a particular sensor for a particular conflict or some sort of natural disaster? What are some of the considerations to do with quality and reliability and trustworthiness, especially if you are, you're operating in an academic setting, so there's pleasing your peers, but especially if you're going on TV and you've got the opinion of the public as well, accuracy, reliability, quality concerns are important.
Yeah, I think it's the main opportunity of satellite remote sensing data sets, satellite derived information on conflict damage or natural hazard induced damages, to provide that kind of lens to the severity, to the spatiality, to the character of a phenomenon. Um, so there's a lot of insights that we can get from that. Of course, the challenge is that it's all remote. We don't have, 1,000 people on the ground documenting their own little pixel or something like that. We don't have that mesh, that human network to report. We are working with integration of social media data and on the ground reporting, but we still to this day don't have a better approach to documenting large scale, like countrywide, like all of Ukraine, like literally every patch of Ukraine. We don't have that sort of spatial coverage, but we also don't have the persistence of other kind of data. There's always gaps in coverage with other systems, in particular in conflict settings. Mobile phone towers go down, electricity goes down, people are not responding as much at night as during the day. So these sort of assumptions of like persistence don't necessarily play out. They're still really helpful in their own way, but they don't give us that kind of systematic data collection that we have with other sensors. So that's kind of why there's unique values with satellite-based observations in the first place. But as far as choosing these different products, it really comes down to the kind of phenomenon we're interested in and the process at play. So the core framing of our work is that there are societal and environmental processes that play out on the landscape, and we use they're manifest in patterns of change and spatial change and temporal change, rates of change. And so again, that's where satellites come in. But then the different sensitivities, if we're talking about change to the urban fabric, change to a vegetated mosaic, or change to forest cover, or change, as we've mentioned, with the reservoir volume levels, that's a three-dimensional displacement or accumulation of water in a fixed place, but it's extremely dynamic over time. Each of those have the different challenges and opportunities for remote sensing. So on the urban side, nowadays radar is just increasingly the go-to system for characterizing urban change, just urban presence, period, but then also urban change. A lot of work has been going into looking at economic deprivation using satellite radar as well as high-res optical data, and those are both uniquely helpful because radar is really the system that is most sensitive to change in or presence, arrangement of features of structure, configuration, your background image there, all of those corners, all of those facets on those building footprints, right? All of those have this, and those are presumably all impervious materials. Those all reflect radar waves in a specific geometric configuration. And there's a variety of different radar systems out there, but they're all, the principle of those is they're all sending out these beams, it's bouncing off something, and then it's being received back, and you can process that in different ways. But those kind of radar systems are really excellent at detecting all the corners, all the roof lines, characterizing that whole cityscape that's behind you. Looking at vegetation, radar can still be helpful there, but radar vegetation changes over time, changes seasonally. And we're also often interested in the condition of vegetation, not just the presence of it, but the condition, the health. And at that point, we're talking about how much chlorophyll is in this thing, is in this plant, and how much of that is reflecting back. So that really puts us into an optical domain where we're passively collecting really the colors of light across different portions of the electromagnetic spectrum, not just visible light, red, green, blue, but near infrared, short infrared, these longer wavelengths, which actually do a much better job at correlating to what we know the sign, the presence of healthy vegetation, what that looks like. That's coming through better in these infrared channels than the visible light channels.
Does that also work for vegetation underwater?
Yeah, it does.
Wow.
That's a different challenge just because you have to get through the water column to detect that. But if you if you're looking not underwater, but at the water column, chlorophyll mapping is how you're going to look at algal blooms. Red tides are a different story. You have to look a little bit different, but still optically is still really useful there.
Interesting.
Um, Underwater, like kelp,
That
even
was what I had in mind. Yeah.
yeah, kelp forests. Optical is very good for that. Very shallow coral reefs you can pull out as well with these high-res optical imagery. Um, I mean, LiDAR is also really helpful for that. But that when you start getting into through the water column, um, all of these things that are present in the water column can basically distort, can impede your clear detection in the same way that we have atmospheric conditions, right? You have haze and smoke and fog and contrails, all these things in the atmosphere above, but we have a whole series of developed atmospheric correction techniques so that even though we are collecting imagery from space, from orbit, and the light is going through in these optical systems, is going through all these different atmospheric conditions, there's a very developed series of basically checks and means of mitigating the influence of those atmospheric conditions on the actual signal we get. With radar, we don't have to worry so much about that because the wavelengths are longer, and so it propagates through the atmosphere really without any disturbance unless you're getting into like a heavy rainfall event, and then the rain itself sends back the radar signals. But outside of those conditions, I mean, that's like the if you have any benefit of radar, it's day or night, regardless of the atmosphere, you can get an image, and you can't say that with optical data. But these all have their different strengths and advantages, and increasingly when you're looking at things like um, vegetation, urban canopies, that's just tough to get because you've got an urban signal, you've got a vegetative signal, all mixed up in some cases in a single pixel or in a ground sampling region that you're looking at. So increasingly, these systems are coming together, not just like look at one and look at the other, but their data is coming together in a single model to help predict, help classify what we see on the ground because um, it's all unique and they all have something to say that's complementary to the other approach.
Yeah. Okay. Just for the purposes of a full and complete audit of all the sensors, I have to ask about another podcast guest, Wyvern, who in the past few months started like an open data program as well, at least to, I guess, maybe for advertising purposes, but at
Hmm.
least you can get some free hyperspectral imagery from them.
Yeah.
So are there any applications for hyperspectral in your lab?
We haven't worked with hyperspectral much. I mean, one of the challenges uh, um, is just accessibility, access to hyperspec data in the right place at the right time. Hyperspec's extremely dense in terms of the data volume. We don't right now have a global hyperspectral mission that gives us like wall-to-wall coverage over time. But hyperspectral data has shown itself to be really useful for things like methane mapping. So th these kind of very particular phenomena processes that really have a very specific region of the electromagnetic spectrum where we do see a signature associated with them. That's where hyperspec is super useful. So it's kind of getting at that level of like doing a mass spectrometer level breakdown, right? Hundreds and hundreds. You slice up the potential electromagnetic spectrum in hundreds of bands instead of like maybe we're working with a dozen, maybe 15 bands typically. But hyperspec gives you so much greater precision about teasing out, really finding these fingerprints, these sort of chemical, right? Like optical chemical fingerprints of different processes. So it's a little bit more, it's commonly used as more like targeted investigations into these specific things. But it's also just really new. So all these new systems coming up, it's exciting to see what can be done because we've never had many choices to work with before, and we haven't had like multiple systems in operation at the same time for comparing and contrasting. But it's definitely like a frontier area of remote sensing.
Yeah. Okay, this is going back a couple of years now, but I should also mention, now that I think of it, we've had ESPA on as well, which is an Australian hyperspectral startup. So there's a
Yeah.
couple if you're wanting to compare and contrast. But
Yeah.
yeah, okay, good to hear
Yeah.
about the limitations too. Yeah.
Yeah, hyperspec is, I mean, everything has their own limitations, but really nothing can get at, like, if you want to look at like toxic metal, heavy metal contamination in soil, like you would have to go to hyperspectral to do that from space. It's just the signal will get lost if you have too broad. If the spectral resolution, it's literally the spectral resolution, you're just getting too much light. You can't figure out exactly what the sources of it. So it's just, the near infrared channel. That's one way you could do it, or you could slice up near infrared into 100 different bands. That gives you much greater specificity to get at that sort of like chemical level fingerprinting for things like specific kinds of pollutants, specific kinds of atmospheric emissions, specific kinds of heavy metals, toxic presence in soils. There's really no way to do it. You'll miss the signal. It's a slight signal in many cases. Like methane cloud is pretty extreme in some, relatively speaking, but a lot of these signals are really subtle, and you'll miss them if you need a very fine-tooth comb spectrally to find them, and that's what hyperspec gives you.
Yeah, the comment about heavy metals got me thinking, because I actually spent the better part of 5 years on a contaminated land cleanup project in the oil field in Kuwait. And we had a remote sensing professor who came from the US and was leading a team for the Kuwait environmental remediation project, which was cleaning up all the contamination from the oil lakes from the Gulf War. And he tried and failed to use remote sensing to automatically detect, where all these old, basically dried out oil lakes were that had then been, in some cases, covered with sand and all of that.
Yeah.
But it made me think, if we had hyperspectral data, there would have been a different outcome from that attempt. Anyway, interesting.
That could have been possible if there is still a presence at the top of the soil column of that oil. If it got buried, it's lost. It's very difficult. You'd have to use some sort of subsurface prospection technique to track it. Coring, right? Core samples, boring.
We did plenty of that, let me tell you.
You'd have to be a direct, not a remote, but a directing investigation.
Right.
Yeah.
Okay, cool. All right, so you've given us a nice tour of all the different tools on the shelf, really. So perhaps we can look at directly at a couple of applications. You mentioned Ukraine. Maybe we can start there in terms of, I guess, for maybe a news service or some humanitarian organization monitoring, sad to say, the progress of devastation.
Yeah, so I mean, this initially came out actually of a collaboration with the New York Times, with Corey Scher and I, who's now a postdoc in our lab, conflict ecology, but was doing his PhD at City University of New York at the time. The New York Times, who we've worked with in the past on different things, but they're interested in trying to develop a nationwide damage map, urban damage map, structural damage map, and of course, this is very difficult to do just because Ukraine's an extremely large country, and you have this, even at the time, months and months and months of damage. So accumulated damage, but also new damage. Didn't just want a before after, want to sort of keep pace with it. So that was sort of the call, is to try to use satellite imagery to map these dynamics, the spatial dynamics, what cities at what time, but also the sort of the pace overall, like the accumulation of damage. So that was months and months and months of work to develop those assessments, and working with the New York Times was quite exceptional because they had resources that typical researchers don't have, and haven't had it in any other project, where they happen to have people in Ukraine reporting on the war in Ukraine. And there are a couple of cases where we had identified something from the satellite remote sensing analysis that hadn't really been, through their reporting at least, hadn't been identified as a place that had experienced a lot of damage. And there's at least one case where they were able to send a reporter to the site and personally check it out, in just sort of like a gut check scenario. Like, are we generally seeing agreement? But but that was a super unique case, and they developed an amazing visualization. The article is called "What Was Lost," I believe. This is out over a year ago, probably now, but um, yeah, I mean that nationwide assessment itself just is such a heavy lift that it's just hundreds and hundreds of terabytes of data need to be processed to do that. So it was quite a lift.
Okay, so yeah, it's a privilege to have someone to talk to maybe in a bit of depth about this. So could you tell us about the sensor choices, if there was anything interesting about any of the analytical or algorithms that were deployed?
Yeah,
If there was any commentary about things that didn't work as well, and how you resolved that, that could be interesting to hear.
for sure. Yeah. This article is just published, so it's on our website, which is conflict-ecology.org. So Corey Scher, who I mentioned, is the first author on this piece. But it's so we use the Sentinel-1 radar. So that is giving us sub-weekly coverage across Ukraine. Ukraine is so wide that we have to have multiple. We do have multiple orbital paths to cover the whole country. So it takes about a month basically to build up that mosaic of imagery across the country. Um, and so we ended up operating about every month. Or we did end up aggregating things every month. And then every month of the war for the first 16 months, we generated nationwide damage mosaics. And the way that the main premise there is that we used an approach called coherent change detection, which is abbreviated as CCD. This is an approach that comes out of earthquake hazards monitoring literature, and it uses a part of, it's a little bit more complex processing of the radar signal where you try to find, in a sense, the agreement of the radar signal, the complexity that comes back to the system from the radar signal. It tries to find how consistent those signals are over time. And so in an urban area, you would expect very high stability, all things considered. A building is built, it stays built. And again, we don't have to worry about the atmosphere so much. So you get the same, more or less the same vantage point. Things shift a little bit, of course, in space. You don't always have a perfect one-to-one comparison, but more or less we're getting the same. We expect to see from the same system, just stability. Same kind of radar waves bouncing off. The radar waves travel about the same length of time to the same features and bounce off in the same way, and we detect that. That sort of structure and configuration orientation, that should be stable. So we established that before the war, like what's the level of stability look like? And sure enough, built up areas, it's all very stable. Then we say, okay, let's take that notion of stability and go into the period of the war from the beginning of the war in February 2022 onwards. Let's go forward and see how this checks out. Does it stay stable, or do we see some changes associated potentially with the war? And so that is where you start seeing this very high stability just drop over time in areas that were bombarded, or specifically areas where there's a ground invasion. That's mainly in the east, right? That's on the front line in the east. So the Russian advance, Corey made this great animation that shows the front line sort of propagating through different cities, and the loss of this what I've been referring to as stability. You would call that coherence. So how it's kind of like, does it cohere? Is it stable? Does it come together? You see this drop in coherence over time.
I understand.
And that's basically
coherence between
that's
passes
the core
of the sensor.
Yeah, it's coherence.
And the loss of
Coherence
that, yeah.
inherently is a change assessment. If something coheres, we're talking about, does it cohere over time?
Yeah, gotcha.
It doesn't just have to be the last observation, but it is definitely an over time question between at least these two observations.
So it's almost like, because we're talking about the classic sort of battle map, and the change of the front, as was the term you used. So that to me, conjures, at least before this conversation, this manual approach with reports from generals from the front, literally. But it sounds like we could almost have uh, the battlefront line drawn in some sense automatically from this processing pipeline you're talking about? At
I
least where it's
mean,
expressed in terms of building damage.
yeah, that's exactly it. So you would definitely be able to track if you were totally blind to the actual frontline dynamics, there's a very strong correlation between the first push of the front line through a city and then the loss of coherence as a which is the
Importantly,
proxy
the
for
first push.
damage.
Got you. Yeah.
Yeah.
Yeah. Yeah.
Yeah. So once it's damaged, then you would have to think about how to. This is really the tricky bit with protracted conflicts is how do you account for shifting that baseline where it's a different state than what it was historically before the war. And so you have to update that reference. In a place like Ukraine, that's really tough to do because it's totally dynamic. Different places have different reference periods that you would need to compare it to. Um, but in any event, yeah, you would be able to at least connect the dots, right, between urban settings. But we use, for that visualization in particular, there's a that's one of the standard products that's publicly available from the Institute for Study of War, is that Frontline. That's a commonly used uh, product, geospatial cartographic product, and that comes from a variety of different, on the ground reporting, human reporting, to try to best assess where the front line is at any day, really.
Okay. All right. That data source, yeah. I mentioned people furiously Googling as we listen. That's another one that yeah, I think people were searching for. It's always interesting to hear about different data sources mentioned by each of the guests that come on.
Yeah.
Okay. That was I mean, of course, there's multiple episodes that could just be devoted to you telling us about this month-long, as you said, analysis. Perhaps we could hear, though, in the small amount of time we have left, how your lab responded to, as many other labs and commercial firms responded to the fires in LA. If you've got some comments about that. Again, starting with sensor choices and analytical methods and the kind of insight and presentation.
Yeah, this was another collaboration with Corey Scher. This was basically when the fire started out in Los Angeles. I mean, I live north of California. I'm in Oregon. Um, it was nationwide news. We needed to wait a few days to get that first satellite image acquisition. But once that was there, we were able to just basically kick into that same mode of detecting, looking for areas of prominent change from the right before the wildfire, the last observation before the wildfire broke out. So in that very first week, there was a lot of on the ground reporting and data collection that had been coming out, but nothing systematic, just because it was such a big push to collect all this data, massive historic fires, and resources were very stretched thin. So there was a reliance on satellite imagery, and there were a couple of early um, hobbyist drone data sets that were coming out, at least to visualize. There's also a well publicized case where seems like a hobbyist drone hit a fire plane in the area. But so all of these sensors were, like kind of, in that case, literally colliding. They were all at play. It was such a well documented scenario, so we could look at it from multiple perspectives, not just on the ground with that sort of post the aftermath, the ground assessment aftermath, which would be done by the CAL FIRE, by engineers, by insurance investigators, by homeowners and landlords and occupants themselves, right? But all the way up to we had aerial SAR, which is UAV SAR, a NASA system. There's hyperspec was run. Any kind of optical system was out there, including the radar data that we use. So we just ran the same estimate, did a couple of quality checks to make sure that we weren't in. The tricky bit there was that there was some background it was a forest fire that spread into dwellings. So there's a lot of variation in that signal just to do with the forest canopy at the edge of this setting. So we had to account for some of that inconsistency. But Very similar approach as we were able to apply in conflict settings, and got some initial estimates that ended up aligning really well with ground-based surveys. And as always, we sort of you get just like a bit of information from one data set, a bit of information from another. So there was just this sort of aggregate accumulation of imagery and also on the ground reporting. But it was a great effort to try to contribute to some of that real time situational awareness. And
Mm.
the data are still available on through the NASA disasters portal.
Mhm.
So anyone
Uh,
that would like to check out the actual maps.
yeah, I think I remember actually first becoming aware of your work through an FT article and some really nice maps in this UK Financial Times
Yeah.
newspaper.
Hmm.
Um, and then I think it was after that when I interviewed Andrew Schroeder that he then introduced me to you. Um, from what I recall, it was really the FT that was the first major newspaper that produced, some, in my view, credible, proper spatial analysis. Is that correct? Via your work,
Uh,
really?
well, as far as like the conflict damage work, the FT is one of
The
the groups
in
that
Oh, okay. I was more meaning about in LA with the LA fires.
um, I actually don't recall which group would have taken it up first, but I mean, coming out of all the conflict damage mapping, we when we put out the LA fires, so it was Ukraine was first, and then Gaza, and then Lebanon, and then LA, and so we have this listserv of journalists and humanitarians that we contact when we have new assessments. And so when that came out, when we did the LA fire assessment, we put that out and shared that, and also put it through the NASA channels, as I mentioned. FT is amazing. I mean, the cartography and the speed at which they make really compelling visuals. We never make those graphics, right? We
I
share
was wondering who
like
was behind them.
no, that's not us. We share like a very small volume, like a few dozen kilobyte JPEG, or sorry, a TIFF or a GeoJSON, like something very simple that's flexibly used across different geospatial platforms, mapping interfaces, whatever. So we just share those raw data. We share building footprint outlines. We share black and white images of damage areas. It's really simple stuff that we end up sharing out. Um, yeah, in some cases, terabytes and terabytes of data that go into that
Yeah,
single TIFF image. But then these newsrooms are just so skilled at making a often very quick turnaround, really compelling, accessible graphics.
yeah. I just thought it was
So
interesting that
yeah.
it was this, foreign for the US newspaper that seemed to be first to the punch, as far as I could see, with this really nice, yeah,
Uh,
visual.
some of that's the
So,
time zone too. We sent the data out at
okay,
11 p.m. here, and they're
fair point.
awake and they pick up with it. Like that
I
happens
see.
too. Yeah.
Right. Yeah. Okay. I yeah would really love to dwell on this more. But given that there's this theme of contact with the media. How do you prepare when a TV station contacts you as a geospatial analyst?
Oh, that's a great question. I haven't really reflected on that. I mean, I think the one thing is that there is of course like an agenda, right? They want to talk to you about something, and so there's
Sorry,
that
I should
initial.
ask you also, as you
Yeah.
answer, which was the first TV channel that prompted you to come?
Well, the first interview that we did was with Democracy Now, actually,
Oh, I love Democracy Now.
on
Great, Amy
On the
Goodwin.
Gaza mapping. Yeah.
Okay, Amy Goodman.
Yeah, that
Yeah,
was the
yeah.
first. And then we had a couple with CNN and BBC as well. The BBC one was by far the most. I was very stressed for the BBC one. But the CNN interviews were great. The Democracy Now interview was great. They're all moved so fast. The conversation really is at a clip. I mean, you can see that whenever you watch a reporter, a professional talking, they have they have it all locked down, their script, and they have these concise statements. So that's really, I think when we did these interviews, we had to realize that way, right? It's all about concision and getting your point across. And it's not about the technical approach. It's just like, what did you find? Why should people care about this? What's new to you? What surprised you? And I mean, obviously, these are all professionals, so they weren't asking. They were asking all the right questions, you know. Um, but some of them were a little bit more statistics heavy, and so for those, you know, I had post-it notes up all around,
Yeah.
like quoting, citing all of our statistics, and citing, depending on the actual thing that we were talking about, which report talked about what level of damage and how does that agree with other ones. So that, I think that was our job in communicating this. We are not there to talk about the politics. We're not there to talk about policy or what should the US do or something like this, right? We're there to say, like, this is what we learned. This is the lay of the land. This is the state of our understanding of this complex situation. This is what we can say, and this is what we just don't know much about. Um, so a lot of our work, we talk much more about the limitations of what we can do or can't do than what we actually can do well. Are we try to be very diligent about identifying something that we can say with confidence, but then also just saying like we can't really comment on that. We actually have no real insight into that, or that's not, you know, the science isn't sufficient enough to comment on that. So a
Yeah.
great example of that is the damage in Myanmar caused from this 7.7 earthquake on the 20th of March. That's extremely complicated to detect that from satellite-based analysis.
Hang
Um,
on. I want to show
no,
that at
please.
least I've been listening to some of the prior guests. I've been trying to find a way to mention this term. In the episode with Sia AI, Alexander Wagner mentioned amplitude change detection. Would that
Sure.
be something you would use in that context?
You could use amplitude change detection. Yep.
Yes.
You could use the coherent change detection approach that I mentioned before.
Okay.
You could do optical overhead damage assessments, which is the
Okay.
sort of go-to, that's sort of the de facto standard for UN style damage assessments.
Interesting.
Um, all of those have their limitations, and some of the radar work in particular is just extremely tricky to tease out when you're talking about um, wholesale transformation of a landscape and trying to pull out damage and identify damage in an area that has displacement due to the earthquake. It's really, really tough to pull all this out, and you end up seeing just a variety of statistics. And you know, we don't really know which one is the right is the most reliable estimate right now because the ground truthing is not possible to undertake. Myanmar also is under control by a military junta that doesn't allow access to certain areas. In fact, has continued to bomb certain regions
Yeah.
where rebels and militia groups are at
Mm.
after the war. So all of this stuff is mixed up
Yep.
together.
And then
All
you
of
add an
these
earthquake to
patterns.
that. Right. Right. Okay.
Yeah, so there's historic damage before the earthquake, like right before the earthquake, and then there's the earthquake, and then there's bombing
Yep.
after the earthquake, and there's no access. There's limited access. There's also often these ground assessments in any sort of displacement scenario come with aid, come with relief, right? You're there to deliver. Humanitarian agencies are there to deliver relief or aid, and they figure out how many people are there, how many you know, what level of support is actually needed given the population and given their needs at that time. And in this case, the government is has been shown reporting is suggesting at least that they're trying to shift the relief and aid to areas that are government controlled, right, away from the rebels, away from the
Yep.
militia. So again, there's no side taking in this. This is the reality
Mm.
of the political situation on the ground, and we try to be aware of that as it guides our analysis because that's a limitation on doing the science. Then you can't get ground truth data because of this political context.
Yeah, I think it's interesting how you have you used the word science there. You are running a scientific laboratory at a university, um, and I get the impression that you're contrasting this, or there's a number of considerations that you have as a scientist, and there's a sensitivity to appearing on television, perhaps, and that there's a risk maybe that, you know, with the sound bite that might be extracted from what you as a scientist are commenting on. there's a risk that, perhaps the public may not get the full picture. Is this what goes on in the back of your mind in some respects, being put in front of a camera?
Yeah, we try to be very, very conservative with our approach. We try to make sure that like the estimates that we produce, that we put out there, we try to keep those in line. None of this is, we're not trying to sensationalize anything.
Mm.
Um, we're trying to, I think, in a sense, try to get the best spatial and temporal approximation of these trends. That maybe it's never going to be perfect, of course, but we try to get it in a realistic way, such that the distribution, even if the magnitude is wrong, which of course it always will be wrong, but the pattern is going to be realistic, that there's not egregious places that are overlooked or overemphasized. And that's really where understanding our limitations are. And it's not just from the remote sensing side, it's also the quality of geospatial reference data. Do we even have an up-to-date
Mm.
building footprint data set?
Well, that's
Like,
another thing. So, because
yeah,
sorry to cut over, but just to mention that when conflicts happen and when there are humanitarian disasters, a common way that the geospatial community may respond is through a humanitarian OpenStreetMap team, tasking
yep,
manager, deployment. So it's nice to have what you're commenting about and all the sensors we can bring to bear on understanding the situation on the ground, as another facet of how our industry can contribute. And I guess what's coming
yep.
through in how you're responding to the camera in your face situation, is that at least we're recognized by the news media as being a resource they can draw on for factual reporting.
Yeah.
Yeah.
Yeah, it's all about it's saying what you can say with confidence that you would back up, right? So even the use of terminology is very important too. An accuracy assessment suggests that there is some truth that could be measured, and you've compared your assessment against some truth.
Yeah.
We never really have that. So we talk about agreement. How well do we agree? But what is my ground truth? What's validity? I mean, even coming from a geographic profession, maps are not truth. Maps are not reality. They are
By definition.
simplifications, abstractions, propositions. So geographers, I'm a
Oh,
geographer,
wait,
right?
wait, wait. I have a book.
Okay. Free the map. There you go.
That's what,
Yeah. Oh,
by
cool.
another Dutchman, yeah, Henk van Houten, is all about that. Yeah.
Yeah, like I mean, we're coming from a discipline where coming out of the quantitative revolution in the 80s, which gave way to sort of modern day GIS as we know it, there's such a recognition of the shortcomings of mapping. Yes, amazing opportunities, amazing benefits, but map making, especially in these interactions with media, that there's an assumption that someone with a PhD must know what they're talking about, that they have to have everything figured out. And expressions of uncertainty, expressions of limitation are not a downfall. They're not a shortcoming of your work. That's the reality of doing work. And in our case, we really feel like there's opportunities to build trust with end users to clearly and consistently communicate the limitations of our work, the uncertainties of our work, which is not just a plus or minus 5%, but the qualitative uncertainties of our work. We know that we tend not to do well in these situations. We tend to have higher confidence in these situations. Like these are kind of rules of thumb, right? We're trying to develop our own internal quality checks for understanding where we can say something with a lot of confidence, and other places where we'll say something, but it's just we know that these factors really impede our ability to do it as well as we'd like. So we are very much like anti-hype. I am the last person to ever say like anything, anywhere, all the time. Just give me AI and SAR. Like that is the last thing I would ever
I've been
say.
wondering if I should ask you about AI.
Our no, AI is fantastic, but it's useful as a tool. It's useful as a way of thinking about things. But AI, data mining, data science at large, we're not going from a foundation of theory to draw out these relationships. We are relying on algorithms that often find statistical correlations and probability density distribution functions that show agreement with some validation or some testing data set that we have. We are not interested necessarily in finding these correlations. We're trying to develop theory and practice around and conceptual approaches to better detect landscape change in conflict settings, to understand the processes that come in there from a theoretical and conceptual perspective, from a multi-scalar perspective, on the ground versus above, disagreements
and a multi-temporal perspective. Yeah,
multi-temporal disagreements between sensors. AI can help you at the very, very end of the day bin those things, right? But we're interested on the front end. We're interested on trying to develop this new theory and science around conflict impact assessments. And AI is a tool that's in our arsenal. We use AI, of course, but there's no go-to, right?
I just wanted. So I have limited time. We've got one remaining minute. But given that you're on AI and the subject has come up in the last 30 seconds or so, sounding like a TV presenter here myself. So a good way to put it, speaking of newspapers, the Wall Street Journal in January wrote an article about geospatial foundation models. Bless these Wall Street Journal reporters. They're always sniffing around, and they tend to be pretty good at keeping up with the trends.
Yeah.
I have also Silurian, a geospatial foundation model startup with Y Combinator funding, coming on the show this week too. So from your perspective as the head of this lab, is this hype, these geospatial foundation models, or do they offer the ability to more efficiently keep track of what's happening in a conflict zone? Would they be useful, God forbid, with the next atrocity?
Definitely helpful. Yeah, I mean, we were working on foundation models ourselves. Cool. Yeah, multi-model foundation model, it's certainly helpful. It's certainly useful. It's trying to explicitly recognize these different complementarities that different approaches have. Different if you're talking about remote sensing, at least. But I mean, I think some of the questions that we ask are not directly answerable. We're not just interested in a detection model. We're interested in the processes at play. We're interested in the pattern is just the starting point. The pattern of detection is just the starting, not the end. Once you have a pattern, you use that to the landscape pattern, you use that to understand processes, which is in a conflict setting, bombing, displacement, decisions made by all these different actors. If you're in a natural hazard-induced disaster, a wildfire zone, that it has to do with the building configuration, that has to do with the temperature, that has to do with the environmental climatic regime. These are the processes that manifest in that pattern. So if you can detect that pattern, then you have this follow-on question of those processes. That's the goal of the work. It's to understand how these things relate to each other in space and time, and why things play out differently. Why something looks one way in Ukraine, why some damage looks one way in Ukraine and looks different in LA. There's a ton of reasons why they're different, but there's a lot of similarities too. And that is one of the foundational things that bridges our these studies is damage is damage. It's manifest similarly as a change in amplitude, as you talked about, as a change in coherence, a loss in coherence. But all these different processes come together to result in that same process, in that same outcome. There's a term for that, which is equifinality. All these different terms, all these different processes come together and they look the same. It's sort of similar to convergent evolution, right? But how is that possible? How do we understand these different ingredients that go into those? Like that's where the scientific research is at. So foundation models, hyperspec plus SAR plus optical, all on board. But the stuff that the questions we're trying to ask are not also they're not just thinking about that landscape. We're really trying to get into decision making, trying to get into operational response to support people to make better decisions in near real time when these data come out. So, I mean, if anything, we're just sort of like, we'll take anything we can get, we roll with anything we can get, but the questions we're asking can't be addressed by a random forest model right now.
And in saying that, you remind me of really the point of Andrew Schroeder's work, and it's about direct relief, for example. getting the right number of medicines to the right location, given their detection of a damaged medical facility. And it sounds like that's a context for your work as well. And that then opens up a whole other aspect of doing, which is the emotional context and impact of, whether or not you're being effective. And that then is, to me, yet another whole episode that I'd love to have. But yeah, it was a huge privilege. All I can say is really the best way to put it is that I feel like, this is just the start. But actually also what I'd like to ask for, because I thought we'd gotten to the bottom of it, about this amazing map in the FT. Could I have a referral to the team at the FT to continue the story or complete the story?
Yes, they always do good work, so we can follow up. But it's always thank you again, Wilfred, for the invitation. It's always great chatting with you. Appreciate you asking these questions and trying to bring some of these different perspectives up. Yeah, really appreciate it.
No problem. I'll get out of your way, being a professor with your next appointment. But yeah, thanks, Jimon.
Thanks so much.